This is Unit 7, Lesson 9 on growth, decay, and compound interest. In Unit 7, we have learned how to solve exponential equations and logarithmic equations. So now we're going to take those skills and we're going to apply them to some real-life scenarios. We're going to have a different equation for each topic here. So you're fixing to look at 3 different equations and we're going to apply those to some scenarios. Our first function is going to be the growth function. And the function is, this is a formula, if you want to call it that. F of t is equal to a times 1 plus r to the t power. So you'll need to make a note of that. Now we need to define our variables. Your a is the initial amount, r is the rate at which it's growing, and t is your time in years. So if they just tell you years, you're good to go. But if they tell you like a year and 6 months, then that's going to be 1.5. If they tell you 1 month, that's 1/12. So anything less than a year, you need to put that in fraction form. Okay? Let's get a scenario and have a look at it. So here we have a problem. An original investment of $1,800 has increased by 7% each year. Write an exponential function to model the situation and determine the value after 15 years. So the exponential function is going to come from our formula right here. We want to find the value after 15 years, and t is time. So we're going to write this as f of 15 equals, all right, a is our initial amount, so that's 1,800 times 1 plus, all right, your rate is 7%. So before you can use a percent in an equation, you have to change that to a decimal. So 7% in decimal form will be 0.07, and then our t is 15. You can simplify this by hand if you want to. 1 plus 0.07 is going to be 1.07 to the 15th power, and then you'll use your calculator to determine the value. 1,800 times 1.07 to the 15th power is 4,966 and 26 cents. And that's all there is to it. Now remember, you have to know the formula for it to be this easy. Now let's look at our decay function. If you notice, it looks very, very similar to the growth function except for one little detail. Now we have a minus sign in here instead of a plus, so be careful. Your definitions of your variables are still the same. A is initial, R is your rate, T is your time in years as well. So let's look at a problem. A $12,000 investment is losing. Now that's the key that tells you you need your decay function instead of your growth. 4% each year. Write an exponential function to model this and determine the value after 9 years. So our time is going to be 9 years. When we write our exponential function, we're going to put f of 9 equals, all right, A is our original investment, so that's 12,000 times 1 minus your rate. And once again, your rate is given in percents, so before you put it in here, you're going to need to change it to a decimal, 0.04, and our time is given in years, so that's 9. Now we can simplify this a little bit by hand. So we've got 12,000. 1 minus 0.04 is 0.96 to the 9th power. And once again, that's going to be a calculator job. When you put this into your calculator real quick, it will tell you that is $8,310.41. If you are dealing with money, you only need to go 2 decimals because that's the cents. So if you're dealing with money, you only go 2 decimals. If you're dealing with something scientific, you need to go at least 4 decimal places, maybe more, depending on your instructions. So now let's have a look at compound interest. This formula is a little more intense than the other one, but that's okay. Some of the words you need to know before we get started. Semi-annually means twice a year. Bi-monthly means 2 times a month. And you will find differing opinions on the word bi-monthly, believe it or not. Sometimes they say bi-monthly is every other month, but in these financial problems, we're going to go with twice a month. So that would be 24 times a year. Quarterly is 4 times a year. Now, let's talk about the difference between the growth formula that we looked at and the compound interest formula we're fixing to look at. The difference in these two is simple growth would mean you invest money and you make interest just on your original investment. So every year the interest is going to be the same because it's going to be based on what you initially invested. If you put in $5,000, you're going to earn interest on $5,000 the first year and $5,000 the second year and $5,000 the third. No matter how much that account grows, the interest is based only on the initial investment. Now with compound interest, it's different. You get interest on your interest. So with compound interest, the first year you would get interest on $5,000. The second year, you're going to get interest on the balance of the account, which would be more than $5,000. So that's extremely beneficial. All right, here's our formula. A, which is your yield, would be equal to the principal times, and principal is your initial amount, 1 plus R, which is your rate, N is your number of times compounded every year, and then your exponent is N times T. That's the number of times compounded per year times however many years you're going to be invested. And it's not nearly as complicated to put this into practice as it is to describe it. So let me get a problem and we'll look at it. So let's have a look. $12,000 was invested in an account at 8% interest. Find the value of the account after 5 years if compounded quarterly. All right, let's take our formula. Our new value is going to be the principal, which was $12,000, times 1 plus. Okay, R is your rate. Once again, we have this in percent form, so we're going to make this 0.08 over. N is the number of times compounded per year. Well, if it's compounded quarterly, that means 4 times per year. So we're going to put 4. Now, N times T, the number of times compounded yearly is 4, times T is your time in years. We're going to invest it for 5 years. So this is what the original version of your compound interest formula would look like. Then we're going to be using the calculator to do all of the calculations. When you put this into your calculator, you are going to get $17,831.37. A savings account offers 0.8% interest compounded bi-monthly. If Bob deposits $300 into an account, how much interest will he earn after 10 years? Okay. All of our data is in here and we're going to plug it into our function right here. So A is equal to the principal, which was $300, times 1 plus. All right, R is our rate. Now since it's 0.08, we have to change, it's 0.8, we have to change that to a decimal. Even though it's in decimal format, that's still a percent. So we still have to move the decimal over 2 places. So our new is 0.008 over, all right, N is the number of times compounded every year. This is compounded bi-monthly, twice a month, so that's going to be 24 times per year. Okay, now for our exponent. N, the number of times compounded yearly, we just figured that out to be 24. Times, all right, our T is the time in years, so this is going to be 10. Okay, we can simplify this sum, or you can put it into the calculator just like this. And when you compute, you are going to get that A is equal to 324.98. Now, be careful, because this problem says how much interest will he earn. What the formula gives you is the actual amount the account is worth. So that's principal and interest. So we need to subtract the initial investment to find the amount of interest, and that's going to give us $24.98 in interest right there. Okay, now hang on just a second. I want to do one more thing. We're going to do a little life skills lesson about compound interest. So to wrap it up, I wanted to give you a look at what the same investment could do figured 3 different ways. Because interest goes 2 ways. If you're borrowing money, this is money you're having to pay back. If you're lending money, then this is money you get or investing. So either way, you need to pay attention to what the difference of figuring your interest rates can do. First of all, we're going to look at a scenario of $1,800 invested at 7% interest for 15 years. Now the first plan is just a simple growth rate, and if you invested that money, you're going to have a return after 15 years of $4,966.26. Not bad. Now, if you invest it with a compound interest, and if that interest is compounded every month, 12 times a year, then at the end of 15 years, you will have $5,128.10. So a little bit more than if you invested it with simple interest. Now, let's look at what a difference, and remember, this is just on an investment of $1,800, almost $2,000, so not a grand deal. All right, next, we're going to look at compounded daily. That's 365 days a year. Now, this is the kind of compounding that credit cards use. They compound daily, so let's look at the difference. Same amount of money, same interest rate, same length of time, would yield $5,143.25. So still more than even compounding monthly. Okay, so that's why it's important to run these through. There are so many calculators online, but I want you to understand the importance of how often your principal is compounded. That makes a big difference. Well, we just wrapped up lesson 9 in unit 7. We have one more lesson to go that will be coming up shortly. So go ahead and do your practice problems. If you need some more practice, let me know and I will find you some more problems. Y'all did great. Hang in there. Bye.